All right, thank you very much.
Yes.
Yeah, so I will show some results about Magnon valves with perpendicular anisotropy. And it's important to say that this work, it's a collaboration between Universidade de Pernambuco here in Brazil and the Massachusetts Institute of Technology, where I worked with the Dr. Jagadish Mudera. And then I will follow these outlines. First, I will show the motivation for this study and why we want to fabricate Magnon valves with perpendicular magnetic anisotropy, because some groups in China have studied these systems with in plane anisotropy, and we are interested in developing them with perpendicular magnetic anisotropy. I will show what is a Magnon valve and how we excite spin waves in these Magnon valves using a temperature gradient. Then I will show some results and anyway, make my final considerations. So first of all, it is important to review what is a conventional spin valve. And a conventional spin valve, as you can see on the screen, it's essentially a system. Looking just to the active region of a spin valve, you have these two ferromagnetic layers spaced by a normal metal or an insulating. And what happens in this system, it's when you try to apply a charge current through the system, the resistance depends on the relative orientation of the two magnetic layers. If you have a spacer layer that is a normal metal as copper, the effect is the giant magnetic resistance effect. And if you are using an insulator, you will see the tunneling process, and the effect is the tunneling magnetic resistance. And these two effects are very important in spintronics, and they were explored in Magnon, in MRAMs, that it's magnetoresistive memories with random access, MRAM, yes. So what happens in this system is that when you have the system with magnetizations parallel, you can use this to say its state is of low resistance, and you can associate it to bit 0. And in the anti-parallel state, you can associate to bit 1. And then you can fabricate these memories, magnetoresistive memories. And so what is a Magnon valve? It's pretty similar, but instead of applying charge currents, we want to excite spin waves or magnons. Magnons are quantum of spin waves. And the other thing is that the system is usually we are interested in magnetic materials that are insulators. So we don't want to charge currents flowing through the system. We want to excite spin waves. And we expect that depending on the relative orientation, similar to the conventional spin valve, we will have transmission of these spin waves that can be a high signal or a low signal. And so we can use these two well-separated states to, transfer information, store data on the media. And so why it is important to work with magnons? As I said, magnons are a collective excitation of spins, and you don't have charge current associated to this spin wave, and then you can avoid the undesirable Joule heating effect. The other thing is that the magnon's frequencies range from giga to terahertz. And so if we are able to control this system and fabricate computing devices based on magnons, we would be able to have faster computers. Also, we can, since we are dealing with waves have frequency, amplitude, and phase, and then you could work with non-Boolean logic operation. You have extra degree of freedoms. Anyway, the spin waves also can propagate through long distances in material with low magnetic damping, as YIG, for example. So magnons are something that we are interested in understand and in control. And Magnon valves could be used to control these spin waves, as spin valves, conventional spin valves, are used to control a flow of charge current. And how we can excite Magnon valves? How we can excite non-Magnon valves. There are two effects to excite spin waves. One is the spin pump effect. And in the spin pump effect, essentially, you put the magnetic material in resonance, and this excitation of these magnetic moments will inject angular momentum into an adjacent layer as a normal metal, like platinum, for example. Other effect that you can use to excite the spin waves, it's the spin-Seebeck effect. Here you use a temperature gradient to excite these spin waves, and then you can excite magnons on a material. And how we can detect these spin waves? The effect is the inverse spin Hall effect, where you can, in a metal as platinum, for example, that has a strong spin-orbit coupling, the material converts this pure spin current into a charge current. And then we can detect this charge current with a voltmeter in lab. So these are the different effects that we use to characterize our Magnon valves. So what we did, the other thing also that it's important to state is why we want these Magnon valves with PMA, with perpendicular magnetic anisotropy, because perpendicular magnetic anisotropy allows a higher density of data storage in a media, promotes thermal stability in these pattern structures where we can store data, also uniform magnetization, and facilitate some spin effects as spin transfer torque effect, spin orbit effect, and Magnon transfer effect. So we really are interested in see what happens when we have this PMA. So what we did, we fabricated these perpendicular magnetic materials. We used the TIG, that's thulium iron garnet. It's a material known to present this perpendicular magnetic anisotropy. Our results showed that it is magnetic, very smooth and epitaxial. And then once we control how to grow this ferromagnetic insulator TIG, we move it to fabricate the Magnon valve. So here you can see a schematic picture of the Magnon valve where you have two TIG or TMIG film separated by a spacer layer of gold. And on the top of the structure, we deposited a platinum film. The platinum film here has the idea of the platinum film is to behave as a spin detector, where we will excite using Peltier to excite a thermal gradient here through the structure. So essentially we have spin waves being excited in both magnetic films. These spin waves travel through the structure. And then at the platinum film, we can detect this voltage that you can see on the screen. And we observe that it's very clear when we control the magnetizations of the two magnetic layers, when they are in plane, or one is in plane, the other one is perpendicular to the plane. We have different signals that is very important to actually apply these systems. We have to fabricate systems that have very clear separated states, so we can control this is bit 0 or bit 1, and we successfully observed what we wanted. We did a study of how these signals depends on the temperature gradient, and it increases with the increase of the gradient of temperature. We also investigated how the spacer layer of gold influences, because essentially the spacer gold layer will control the strength of the connection between the two magnetic layers. And I think my time is almost there. Anyway, so the idea of my work to make my conclusions was, first be able to fabricate and characterize these Magnon valves using TIG, that it's a rare earth iron garnet that presents perpendicular magnetic anisotropy. The fabrication process itself is not so simple to create these tri-layers with PMA, but we did. And the second part was to show that we can effectively excite spin waves in these structures, and that on top of the structure, on this spin sensor, that's the platinum film, we really can see that the signal that arrives there depends on the relative orientation of the two magnetic insulating films. And we did this. And so we hope that we will keep, moving forward, and we could give contributions to apply these systems in wave-based computing devices. Thank you.
Thank you so much. If there are any questions, please go ahead. In the meanwhile, I'm actually curious. You keep mentioning the fabrication process is hard. Can you give us a little bit more details of how that works?
Yeah, the process itself, it's not so hard, but get this PMA is hard. We use the sputtering technique and some, some evaporators to grow gold. But the thing is that the TMIG film, it's not, it doesn't show PMA unless you make a annealing treatment, a post-growth treatment.
I see.
And so you have TMIG, gold, and TMIG, and it's quite hard to, in this structure, to hit a nail in the right temperature to get this PMA, because gold may diffuse into the TMIG. So you have to, try a lot until you get the right conditions to grow and show that you have these two separated hystereas for each TIG.
Right.
The film is still there and it's uniform, so you can, flow spin waves through it. So it's more about post-growth processing that it's tricky.
Right. There is a question from Said. He's asking why was gold selected as the buffer layer between the two TMIJ?
Yeah, because of the AtC parameter. We wanted the top TIG to be epitaxial and shows PMA. And we try to do it with platinum, for example, that I agree with Said, that's better to transfer spin waves through the structure because platinum is better than gold. But the AtC parameter is something that influences a lot when we try to have these two layers with PMA. That's another question. TMIG is sensitive to the orientation such the YIG. It's sensitive to the orientation. What do you mean? Do you mean anisotropy? Depending on the direction. Usually YIG films will show in-plane magnetic anisotropy, and YIG for spin waves has a lower magnetic damping. YIG is the best one, but damping and magnetic properties, yes. And TIG, it's the damping TIG is not so low as it is in YIG, but we still can see spin waves on it. But it's hard to get PMA, perpendicular magnetic anisotropy, in YIG films. That's why we chose TMIG. I don't know if I answer your question, but yeah, thank you to Rodrigo. Yeah.
Okay, thank you again, Golvenia, for your great talk. If there are no more questions, I would like to encourage everyone to go to GatherTown for the last GatherTown session of the conference. We can all chat there for a little bit more. As you said, last before the party.